Okay, for the last video, we're going to cover an example in depth of variance and standard deviation. Now, one of the key things here is that just like this entire course, this is cumulative. So in order to get standard deviation, you need to be able to get variance. And in order to get variance, you need to be able to get the mean of a given set of data. So let's just do a fairly quick example and talk about what we're looking at. Now the first thing I want to do is examine the formula for variance. So variance, if we're talking about a population, we're going to represent it like that. If we're talking about a sample, capital S squared. So again, population parameters use Greek designation, and we'll use letters like S or even some other shorthand for samples. But either way, the variance is going to be represented this way. And the formula is, again, excuse the handwriting, going to be this. Now, what exactly are we looking at in this formula? Again, when I say x bar, it's the same thing as mean. I'm just used to writing x bar, where you're probably used to seeing m for mean. So what the formula is saying, if we look at it in depth, is when we think about the average for a given set of values, one of the shortcomings of using the mean as a descriptor of the central tendency for a set of data is that that value may not actually ever occur in the data set naturally. So if we look at a class grade, maybe the grade is 77.8 as the average for the entire test, but nobody in the class got a 77.8 or whatever. So variance in any measure of spread, variance and standard deviation both, they're very related. Of course, attempt to talk about the fact that, hey, not every value is going to occur on the mean, so how far away on average are the values from the mean? How spread out are our data? So that's what the variance and standard deviation subsequently are attempting to quantify. So when we look at the formula, let's look at the top, just inside here first. We're saying x minus x bar, or x minus the mean. We're saying I want to know the difference between my individual raw data points and their average, the average for the whole set. Because again, we're attempting to quantify how far away from the average is my data. So x minus x bar attempts to get at that. We'll talk about where that square comes into play, but we want to know what it is for the entire data set, which is why we're going to sum it, obviously. So we are attempting to quantify the average distance between my raw data and the mean. And variance and standard deviation are related, and this is what they attempt to get at. We're doing that, of course, accounting for how many that we have, how many that we're estimating. So think about the formula as we go through this, because what it's telling us is, hey, how far apart from the mean are my data? So let's take a made-up example. Let's say that there was a test, a statistics test taken a few years ago, and there were only 6 people who took this test. Their grades were 80, 77, 91. 2 people got 88s, and a 72. We want to know the variance for these data. Now the first thing we'll need to do is, again, going back to a formula, we need to know the mean for this data set. Hopefully you have no problem doing that. The mean would simply be adding all these numbers together, dividing by how many there are, which there are 6. And if we go through that calculation, we'll see that the mean, or x bar, is 82.7. Now again, this just clarifies and details how our average was never obtained by any of the individuals who took this test. So we want to know how far apart are our data from that average. So one of the things to get in good habit is, let's list our data vertically here. And you don't have to do this when calculating variance, but it's not a bad idea to. I'm just going to sort these down descending. So again, these are all the 6 grades that were obtained, and I'm just writing them down from highest to lowest. Okay, so I want to know the difference between those values and the average for the entire data set. So we already obtained the average represented by X bar here. And we're going to write that down, the average for each one. Now, you might get slightly, and I mean very slightly, different results depending on how many decimal places you round to. I'm only going to round to 1, and I believe on your exam all of your answer choices are also just rounded to 1. So I'm just going to stay consistent with that. Okay, so again, I want to know the difference between each of my individual values and the mean for the entire value for the entire data set. So I'm going to represent that as a new column over here. And this column just represents the difference between my data and the mean for my data. Alright, so if I did 91 minus 82.7, I get 8.3, 5.3 for both 88 minus the mean. Wrote that down wrong. Now here, when we get to 80, 77, and 72, and we're subtracting the mean for those, you notice we get some negative values. Those negative values are an issue. Now, the reason why those negative values are an issue is because if I were to stop here and say, hey, I've got the difference between my mean, not my mean, I got the difference between all of my values and the mean for the entire data set, this tells me how far apart they are. And you want it on average for the entire data set. There's a problem because if you do add all of these up, you get 0. The reason being is because those negatives cancel out all the positives. Raggy. So what we want is some way to get rid of these negatives, because we can't really accurately quantify the average distance between our data and the mean for the data if they cancel each other out. So that is, when we go back to that formula, that is where that square comes in. That square will get rid of new color. That square will get rid of those negatives. So all I'm going to do is square each one of these values. So 8.3 squared is 69.4. 5.3 squared is 28.4. And I've got 2 of those. Negative 2.7. This is where it gets beautiful. We get rid of that negative sign by squaring it. And now we have 7.1, 32.1, and 113.8. Okay, so now we have no negatives. So if we add these up, we will not get a 0. So sum all of these, and we get 279.3. So the difference between all of my values and the mean for my entire data set squared is 279.3. That is also known as the sum of squares. You don't have to know that now. That will come up later, a few weeks down the road. But again, we have just gotten the difference between the values and the mean. We have squared it, and we have summed those squares. That's why it's called sum of squares. So going back to, without going back to the formula, let's rewrite it here. Variance, again, population here, or sample here, is going to be the sum of squares divided by n minus 1. So here we have the top part. So 279.3 divided by n minus 1 gives us the variance. Now, N, again, just represents the number of values we have in the raw data set. Remember, we had 6. So that is just saying our sum of all those squared differences. 6 minus 1 is just going to be 5. So 279.3 divided by 5 is going to give us our variance, and that variance is 55.9. And again, I'm writing both of these because it depends on whether we're talking about a population or sample. If we're talking about a population, expect to see this. If we're talking about a sample, we'll see that. But for this course, calculate them both the same. Okay, so this is cool and all, but if I say the mean of the grades on this test was 82.7 and the variance was 59.9, 55.9 what? That's the problem with variance. There are no units here. So it's not too meaningful. Later on in the course, we will work with variance very extensively. So variance is wonderful and useful. But if you're talking about this in terms of almost like in layman's terms, how can I describe my data? Variance is less useful. And it's because it is missing units that the data are in. Well, fortunately, we have the standard deviation. The standard deviation is going to be represented with, again, that or this, which if you'll notice, the only difference is, let me write it the other way around to match up. The only difference is it does not have that square. So how in the world do you get rid of that square? You take the square root, and that will get rid of the square. So the formula for the standard deviation is the same as the formula for variance. You just go one step further, and you take the standard deviation. So the full formula, again, would be the same. But that whole thing would be under square root sign. And that would give you your standard deviation. Now, we've already gone through this part up above, and you got 55.9. So, if we wanted the standard deviation for these data, then depending on whether we're talking about a population or sample, we would just take the square root of the variance that we found. And we found that up here to be 55.9. So if you take the square root of 55.9, you get 7.5. Now, 7.5 is meaningful because it's in the same measurement unit as our raw data, or our average. So when I say the average on that test was 82.7 points, the standard deviation is also in those same points. So I can say, hey, for the test that was given, 6 individuals took it, their average was 82.7 points. Standard deviation of 7.5 points means on average people scored 82.7 points, give or take 7.5. They all scored sort of within that range, anywhere from 82.7, 7 or 8 less than that, or 7 or 8 higher than that. Most people fell within that area. So that's how you get the variance and the standard deviation. It may be helpful to think about what it is you're doing, what it is you're attempting to find with that formula. And again, that is you're trying to quantify and describe the fact that not every value is going to fall on the mean. So we want to know how far away from the mean on average do our values fall. That's what variance and standard deviation give us. They both are measures of dispersion or spread, variance, heterogeneity. But standard deviation goes one step further, and it gives units to that spread that put it in the same, basically the same language as our values, our mean, our data. All right, so that concludes the review for this. Hopefully you found it useful. Watch these videos as many times as you need. The test opens at 5 a.m. Friday, September 8th, and it closes 11:59 p.m. Saturday, September 9th. So get it done in between then. Let me know if you have any questions in between then as well. Thank you for your time.